Welcome to the course on two-dimensional signal processing, principles and practices. We had done this DFT, 1D and 2D, and also the convolution, linear and circular convolution, and the relationship between them. So to do, if the signal is very large, you want to convolve that signal, or the length of the sequence is very large, then if you want to convolve it with the filter or the impulse response h of n. So in that case, in 1D and 2D, what are the ways in which we can do that? Also, how do we use the DFT and the circular convolution? And what is the method which helps in finding the filtering process of the 1D and 2D sequences using overlap add and overlap save methods? We'll see it today. And the overlap add and overlap save methods are the direct convolution. When we want to take for a large sequence, as the signal is captured, the sequence length is large. If it is small, that you can do the convolution easily. But h of n would be small, but the signal length is large. If we are talking about the 1D case here, then it is computationally expensive, and also the efficiency can be improved by using the DFT, splitting it into smaller sequences. So if we take in the case of image processing, the image size is large in case of 2D, and then suppose 512 by 512 or 1024 by 1024, but the filtering kernel would be very small, like 3 by 3 or 10 by 10. So in that case, we have to split the image into smaller sequences and perform the convolution to this h can be of any filter kernel. So this can be fit into the filtering process. So this convolution process for a larger size or the larger length sequences, how do we perform it? That's what comes into picture of overlap add and overlap save methods. So in this, the DFT size, which leads to the circular convolution, we can use DFT also for this convolution. And then what are the aliasing errors? How do we avoid that at the boundaries? That needs to be taken care in the overlap add and overlap save method. So let's look into the two efficient way of doing this convolution, is overlap add and overlap save. And these methods, because we are segmenting the sequences into smaller size, it would reduce the memory and computational complexity as well. So now we come to the overlap add method, so in which the overall, suppose x of n, which is having the length some capital M or capital N length. So we segment that to a length of smaller length of L, and then the discrete time sequence for which that convolution needs to be performed is M. So obviously we know that a linear convolution of this L length and M length, the resultant would be L plus M minus 1. So in this, so when we segment this L, that is x, so x is segmented into x1 plus, we can have it x2 and into h1. So in the h we keep it as such, that is a smaller sequence. So the x1 and x2 split into two, the x sequence, and then we convolve each one, that is h with x1 and h with x2, and give this convolution individually. So this is fitting into the additive property. So now getting into the one example, that x of n is having a length of 10. Suppose this is a sequence. So it's a smaller sequence, but still, for example, to show it here, we have taken this 30 minus 20 to 10 minus 2. This is the sample length which is having. So can we split this into x1 and x2 and h of n? So this h of n is here 2 to 1. So the length of h, you can see that this is smaller, and where x can be split into x1 plus x2 of equal length, or the length which we can fix it. So how do we perform the convolution for this? So it's easy that x plus h so can be done with x and h. Linear convolution can be done, but splitting this into two sequences using the additive property, and then how do we do this? So that's nothing but the overlap add method, in which we have the h of n length is equal to M equal to 3, and the block size we can have this 6, because the resultant is going to be resultant n, it's going to be L plus M minus 1. So M is known, which is 3, and this is minus 1, and L needs to be fixed That means the segment length needs to be fixed. This can be fixed by knowing the result of the convolution. N is going to be 2 power of something. So 2 power 4, 2 or 2 power 3 or anything. So here let's take this 2 power 3, that's going to be 8. So in that case L equal to 6. This is also the way to fix the segment length L. So this N will be used and the DFT size would be this 8. So now we have we are going to segment this X into L segments. Then so what we get is the first 6 points of it, that is 3 0 minus 2 0 2 1. The second sequence 0 minus 2 minus 1 and 0. So the second sequence, that means from X only we have taken X1 and X2, and the linear convolution of each block with h of n. So what would result X1 convolving Hn, that is linear convolution, which we know that is how to perform this convolution. We had seen already in 1D convolution, linear convolution. So the resultant output will be 6 6 minus 1 minus 4 2 6 4 1. So and similarly we perform X2 with H also in the next step. X2 and H, the convolving it linear convolution, and then we getting the output as this 0 minus 4 6 cents. So this is length, because length here it is 6, because this one has only 4 points, the rest of the 4 points of the X. So it's not equal to 6, we can make it 0 0, so that it will also give L plus M minus 1 8 points here. So that's not going to be of any use here. So we have just taken the length what is left over from the X as X2 and convolve it with 2 to 1 linear convolution. So in the overlap add method, what do we do? So X1 and X2 are taken, X1 and X2 which were convolved with H resulting in Y1, that is this one from the previous case here, one, and then the second one Y2 of n, that is Y2 of n is 0 minus 4 minus 6 minus 4 1. So to the length of L, so shift this Y2n and then trying to overlap last M minus 1 samples which we got it Y1 and Y1 and first 2 samples here of Y2. So we take this block and add these points also. So how do we get Y from this Y1 and Y2? So we have convolved it. How do we get this Y of convolved sequence of X and H finally? So the Y of n equal to this 6 minus 1 minus 4 2 6, and then this 4 plus 0 we have to add it. That's why it is called overlap add. This overlap is added, the samples which are in this block should be added, and 4 minus 4 and 1, so gives you minus 3 and minus 6 over here and just adding it. So this is the resultant convolution of the sequence X of n convolving H of n by splitting X into X1n plus X2n and convolution of each using the additive property. So this method is called the overlap add. To generalize this method, so how do we generally do it? So taking an input signal and split that into L sequence, we have told that how do we decide the L here. Okay, so L needs to be the total n length sequence this n should be at least the 2 power, so that L can be decided. So L and L segments, different L segments. So this is X. So this is the sequence X. In this we are talking about in 1D. So X1 n, and then you have M minus 1 zeros. You can append it with M minus 1 zeros. So X2 similarly append it with M minus 1 zeros, and X3 M minus 1 zero. So in the segments we have. So if 6 is in the second case X2, it is that L, we can add M minus 1 zeros in X1 and X2 as well. So after this adding these zeros, and what we do is the convolution X1 into H, X2 into H and X3 into H. So the resulting sequence is Y1n, which has this M minus 1 points here, and similarly X2H also has this M minus 1 points at the beginning and the end, and similarly here. So as we write this Y1n, and Y2 should be starting with this point, should be writing that Y2 in this way as we have shifted in the previous example, and then Y3 if you have any segment, that should be, and Y4 if you have another segment, that can be written from this point. So now add this last M minus 1 points, add these points, and if you don't have, just leave it as such. So that these points, this added points needs to be collected from here So you would get y as we did in the previous example. So this is to generalize it. So now can we use this DFT for performing this convolution? So we need to have this 8-point DFT, that here n we have computed like in the previous case. We take this example and zero padded the block length to 8. Okay, so I think you now understand that DFT thing, it is a circular convolution. So we need to make it n equal to 8, that is block length. X is equal to, then now we can see that the 6 length is x1 is appended with zeros, and the 4, which was the x2 length in this example, made 8. You can see this 8 0 0 0 is appended, that is 0 padded, and then h also make it equal size 0 padded. Okay, now we perform the DFT of x, that is dx1k, x2k and hk. So x is xn length is split into x1 plus x2 of I is varying from 0 to whatever the length signs n. So performing this xi to 0 to 7, then suppose this is 1 and x1k would get, and if it is 2 and you would get the x2k, and if it's 3 x3k. And so in our case it is only 2 sequences, 1 and 2, and h of k, which is from the h of n, we get use the DFT equation we had seen already and get this xik. So xik, so to get y1 we get x1k into hk, multiply them, that is nothing but the circular convolution, that's right, in the time domain. So now this is the case. Now for x1k, what we got, that DFT of the x1k, these are the complex numbers we got, and x2k similarly second segment, that is x1n and x2n, the DFT of this with the appended zeros, that is made n equal to 8. For this 8-point DFT is taken, and these are the results of the 8-point DFT, where from this we can get the magnitude and phase spectra, or real and imaginary spectra, these things that we had obtained for an example. So here the x1 and x2, and similarly h also we can take the DFT, 8-point DFT, and then now we perform x1h, get y1k, and this is the multiplying this x1 and h here simply position wise, and then we get this. Similarly x2 and hk are multiplied to get y2k. So this is the result of this multiplication, and now we have y1 and y2k. So after this, compute the IDFT, because we have to bring back to the time domain. So this YIN is YIK is known, and individual YIN can be obtained. Here Y1N, so if you use the IFFT command, you would get that as well. So this is the sequence which gives 8 point from the Y1K and from Y2K. So if we take the time domain sequences, so these sequences, how do we now get Y of n from this? Help in that. So shift this L block, so Y1 plus Y2n minus 6. So what we got is Y1, and then Y2 is this, and we add it as we have told there. This two last m minus 1 points needs to be added in the overlap add method. So that's how we get 6 6 minus 1 2 6, and this is 4, 1 minus 4 is minus 3, minus 6 minus 4 minus 1 0 0. So this is the result of the convolution of this x and h, which we had obtained through the linear convolution. And when we use the DFT, we actually having this doing the circular convolution just to make this linear convolution equal to circular convolution. That's why this 0 zeros are appended in the sequences. After adding this, get the y1n and y2n, and then add it in this fashion. This is overlap add method using DFT. So to get this summary of this overlap add method, what we the first step is to break the input signal x of n into xi of n of length L. So this length is decided by the n which is known, can be closer, we can choose L plus m minus 1, and 0 pad h of n also to this, because h of n is a small sequence even in 1D and 2D also. So compute n point DFT of h of n to get h of k, and each block xi n compute the DFT of it. That is xik, you have to compute x1 y1 corresponding to that, x2 y2 corresponding to that, whatever the length I we have. So that so many blocks of segments, the signal has been divided. In that compute, then yi, each block, this one take the inverse DFT, so that y1n, y2n and all of this would be obtained. And then m-1 samples, this last m-1 samples, how do we add it is that yi-1 that we had shown through the block. So now coming to the 1D overlap save method. So the performance can be verified with the overlap add and overlap save methods. Here the same sequence we will take x of n 3 0 minus 2 0 to 1 this and h. So compute this convolution using the overlap save method. So x1 we had already splitted the segments L equal to 6 and x2 also. And now what is the difference here we have with the save method corresponding to the overlap add method? Here we need to add m minus 1, that is m is coming from h, the length, minus 1, 2 zeros at the beginning, so here of x1. So what we have is x1n is now, you can notice that there are 2 zeros added before this, and then have the same sequence that what we had. Then x2, what we had, this repeat this m minus 1 of the previous sequence again in the x2. Okay, so then have this portion which is over here. Okay, and then again this is appended with zeros. Okay, so you can see that here to 1 0 0 0 to make this length 8. Okay, so this is the length 8. Now this 0 2 1 and the 2 1 is repeated over here, and then the 0 0. So from take now x1 and the h, we are not going to do anything on it because this is just used for this convolution. x1 and h convolve it, linear convolution, then get y1. So now you can see this, it's not the simply 6 6 what we got in the previous case. We have this appended zeros reflecting in y1 as well. Okay, so to collect it, then y1 needs to be discard this that first m minus 1 samples, and because this is repeated in the second sequence as well, the x2, so this last two m minus 1 samples should be discarded. So we get ultimately this portion only for y1, and take the second sequence x2, and which is repeated from this m minus 1 and repeated from the first sequence, and there are zeros added to it. So now perform x2 and h, the convolution, and we get the sequence of this. In this case, similarly, you can discard these two and here as well because we don't have the other sequence. So the rest of this 4 minus 3 minus 1. So this is the sequence which is obtained from the convolution. Now y1 and y2, append them, like not adding them like in the overlap add method. So the first sequence which is taken here, append both, that y1 and y2, 6 6 minus 1 4 2 6 4, and then here 6 up to 6, and then this is the second sequence which we got here. You can see this one, this would come here, and the previous sequence from which this y1n and this is y2n. So these are the, just appending this after discarding the m minus 1 samples values. So this is called the overlap save method, and if we use the DFT for it, like using DFT, take the x1 as such and x2, and we have already obtained in the previous example. So here x1 and x2, you can see this is the m minus 1 zeros, and after that the L samples of this x of n, and then 2 1, this is repeating x2. So for this sequence we need to take x1 DFT, x1k and x2k. Similarly, this is also 8 point, these are 8 point DFT is taken. So this the output of the DFT is complex values, and the redundancy of them can also be observed. This 2.701 k equal to 1, it can be here also, this 1. So this complex conjugates you can observe, okay, and this is the center one. So you can see the redundancy of this DFT as well in the x1k and x2k also, in the DFT output as we have learned the DFT properties. Similarly, x2k, for which take the DFT, and then now h of k, that is hn what we had got from that, take the DFT of it. So now multiplying this x1 and h as we did in overlap method, also y1k, similarly this result would be h and x1 would result in DFT of this. So this DFT is different from the y1k which we obtained from in the previous case. So this one, and similarly y2, x2k and hk, multiplying it and get the complex values again. And for y1 and y2, we have to get the convolved sequence. So multiplication, we have to do the inverse DFT, get the sequence 4 1 6 6, this one, and the y2 one is this. Now how are we going to append it? Is the first two samples needs to be discarded, so that is discarded, and rest of the sequence here is put, and then here the first two samples needs to be discarded, and then the rest of the samples should be appended. So the case of if you use the DFT, that initial 2 m-1 samples needs to be discarded. So this is we can perform this using the circular convolution as well. So that will be equivalent to what we got it through the DFT. So perform this individual circular convolution and get the y of n of this sequence, that is adding it together. That means these two, and then here should be neglected, and then 4 6. So these two should be neglected, and the remaining will get here. So this is appending there. So when we perform the convolution in time domain, take care of this both the sides, and when we use the circular convolution, only the using DFT especially, then only the first m-1 samples needs to be discarded. So to visualize this overlap save method, here you have the zeros, and these are m-1 points overlap. Okay, so length you can see it goes up to this point, and here this is repeated over here, and this is repeated over here in the segment length x1, x2, x3. Then perform the convolution with h, or use the DFT method. The y1 and y2, y3 you get, and this needs to be discarded, and then here the first m-1 samples needs to be discarded if you use the DFT. The case is last two m-1 also should be discarded if you use the time domain convolution. Okay. So this is the overlap save method, and to consolidate this method, insert m-1 zeros at the beginning of sequence xn, and break the input signal into xi n. So you get the n equal to L plus m-1, the overlap length is m-1, and 0 pad h of n also, this is using the convolution using the DFT. So n point DFT of hn, take this, and individual DFT of this xi needs to be done in the next step. That is, you can have xik, similarly multiply this xi with h, individual hi, and then compute this y of I, or here y of I, and each cases, and discard the m-1 samples. So that we have already done. So this y of n, appending them, just discarding the first m-1 samples, and that is last in the case of if you have the convolved sequence. So this you get the y of I n, appending them individually, get y of n. So now coming to these methods, overlap add and overlap save method, how do we apply to the two-dimensional signals? So the two-dimensional signal, so we have to just extend the method as we did in the 1D. So now x of n, here x of n1 comma n2, this one should be divided into many segments. That L segments of the length is I comma j. So I and j are here varying from 0, I is varying 1 to L1, j is varying from 1 to L2. The segment is 1, 2, 3, 4, like that, both directions we need to have. That means you will have a small square, or if N1 and N2 are equal. So you can have this L1 and L2 segments, and xij and xn1 comma n2. So this is how x of n1 comma n2 is. So if you add all this together, all the pieces of the two-dimensional sequence, you would get back this x. Okay, so this is dividing the sequence in the two-dimensional space. Supposing we have n1 and n2. So if we have this this sequence, then divide this. This is the sequence X, and these are the small pieces of it. So you can divide this sequence into the small ones. So these small ones to be compared with N1, N2, that is having the H, the impulse response. This impulse response and convolving this one to with the impulse response and impulse response and impulse we get each one the convolved sequence. So now deciding on that, L1 and L2 is the number of segments of this image. Okay. So now convolve the X H convolution, the whole image, it's equivalent to convolving these individual small pieces into H of N1 comma N2, that is into the convolution here. So what we have, this is L1 is varying from this convolution, so of each one can be represented this way. So how do we choose this? The region of support for Xij n minus 1 is much smaller than the X. So we have to, you think of L and think of the length of the sequence. So if X is having a length of N1 cross N1, a big image, this Xij should have the region of support smaller than that. At the same time, we can have this M. So we have, it should be comparable to this region of support to M. Okay, this is a big image, and this size needs to be comparable to this one. It can be little greater than this M. Okay, a little larger than this, but it should not be much smaller than M also. Okay, so we need to choose this segment length L in such a way that it should not be less than M, and it should be should not be like N. It should be again at least less than N. Okay, so less than N, but it should not be again very less than M. Okay, so at least it should be little greater than this M. So the length chosen, the region of support X11, 12, 13, 21, 22, 23 are named here, this X image. So how do we get this X, the convolved sequence X 1, 2, 3? Okay, so you can see the length here n minus 1 and n minus 1. This is a square image, that is n1 and n2 are of equal length. So and similarly the impulse response H as m minus 1 and m minus 1. So in that case, first what we do is take X, the small one, and in H, that's convolve this and get X n1 n1 comma n2 and H n1 comma n2. So this convolution of these two is put over here, so the corresponding position, and we will take the next one, that is X21, this portion here, and convolve it with H. Okay, that is H of n1 comma n2. This is 2D convolution, linear convolution, and we had done already this linear convolution, and keep that in that portion. This is different one. So here this is 2n 21, and then we go for the other one X12, this portion of the image, X12 n1, to convolve it with H of n1 comma n2. So we get this particular convolved sequence, that is here, and then we have the last one, that is X22 H of n2. So we can similarly extend this same idea of convolving pieces in 1 3 2 3 3 1 3 2 and 3 3 as well. Okay, so now after performing this, how do we make this as a single image which is convolved? So now if you just put that in their position, as we had seen in the overlapping case, that m minus 1 samples are getting overlapped in the overlap add method in 1D. So this portion is overlapping. This you can see the overlapping here, overlapping here, overlapping here, and overlapping here. So these portions should be added. Whatever the samples are there, as we did in the overlap add method, this needs to be added. This samples should be added to get X of H, X and H here, X convolution H. So this would be n minus 1 and n minus 1. So this is how the overlap add method is done. So we are simply extending the idea of this 1D to in the case of 2D. So overlap save method, if we take the overlap save method, in which consider this X dash n1 comma n2 should have this the region of support n1 dash and n2 dash, we can see from X of n, that is n1 and n2 that we had. So how do we again H is having the region of support m by m. Okay, so choose this. Here also should be x dash should be sufficiently large relative to m comma m cross m h, but sufficiently small relative to the image size n1 and n2. So it should be definitely less than n1 comma n2, but at the same time it should be larger than m1 and m2. So choose in that way, and then go to the this is the condition of m1 and n1 dash should be in between, and m2 and n2, this is impulse response size and this is the image size. So this n1 dash, the segment length should fit inside in this condition or inside this value of m1 n1 and m2 n2. So then convolve it, that is make this n1 dash and n2 dash in such a way that so you have the circular convolution equal to the linear convolution, so that DFT can be used here. So m1 dash, m1 minus 1 and m2 minus 1. So this is the condition in which this would be equal, right? This linear convolution equal to circular convolution. We had already seen that. Now, how do we do this overlap save method? So now take this x n1 comma n2. So what? Suppose this is a piece of sequence x2 3. It has x11, x12, 13, 23, 31 and so on. Suppose we take this case of x23, okay, and append it with m minus 1 zeros and m2 minus 1 zeros here, and make this piece of image this size n1 dash and n2 dash, this is the piece of image, but extend it to the as we did in the overlap save method, appended with the m minus 1 zeros, okay, and the m minus 1 zeros and the here also m2 minus 1 zeros, okay. And what we had done, n1 dash and n2 dash, this is the size. So now we have this piece of image and convolve it with h, that is m1 and m2. This is the size of the h. So now convolving this to circular convolve the two, because the size is made equal, so we will get this size, okay. Circularly convolve them and get the piece of y23 which is having the shaded portion also along with that, okay. So similarly y1, if we take y1 will have the another portion, y2 will have the other portion, and y13 will have some portion of it, and y4 will also be having that portion of it. So then we can discard that portion, okay. So as we did in the case of overlap save method, the zeros and the repetition of the last sequence, okay, in the first m minus 1 sample and the m2 minus 1 samples to be discarded, so that we can get this y23 and y22, y21 and so on. So this is the result of the convolution, the overlap save method. The circular convolution property, we need to have the case of n1 dash and n2 dash with this length, so that we can use the circular convolution. Otherwise, this won't be able to give the length properly, or we can use the DFT for it to get this back. These two methods helps in saving the computational complexity. Instead of performing this take image with H, the kernel, the convolution, we can use the DFT, one thing, and segmenting it will make the pieces of DFT or the linear convolution in that case. So overlap add method is much easier compared to the overlap save method. Now you can see the last m minus 1 samples in 1D as well as in 2D, that should be just simply added in the case of overlap add method. The different pieces of convolved sequences are DFT, using DFT, multiply it and then get the inverse DFT and those piece of sequences, and simply overlap it and then add the common points. That is overlap add method. In overlap save method, you have to discard certain samples and you have to have the previous sample one should be following m1 minus 1 and m2 minus 1 should be following from the previous samples. So that needs to be discarded in the case of overlap save method. So the more practically overlap add method is used because it is very simple to use it. In both the methods, the segmenting operation of the sequence helps in finding the convolution or the filtering operation easily. That computational efficiency point of view, these two methods are being used. Thank you.